This is over. I sent out this website. You've all seen it, I hope. The syllabus is here. In this class, we do mainly electromagnetism, charges, and circuits, and we get into optics as well. We'll have sound at the end of the chapter, mainly because we didn't do sound last semester, and I think it's important for you to have sound, especially for you pre-med students, because you might see sound on the MCAT. Not going to do physics, modern physics or astronomy. I have our dates for our exams here. Please go ahead and set those aside. And also, we're going to have like a little pre-exam, if you will, on January 25th. That's a week from today. It's not going to be, it'll be graded, but not graded. You understand what I'm saying? Like, you're going to get it back as a grade, but it's not going to go into your grade. It's just sort of a place for you to, okay, I'm just going to take this little mini exam and see how I do. All right, so I would, if I were you, treat that like an exam, like treat it like it's, you know, your life depends upon it. Maybe not your life, but treat it with respect and prepare for it. We'll have that next Wednesday, mainly because I'm out of town. I'm on a committee to review the science content standards for K-12, and we have to meet. So my wife is going to come in, and she's going to give you the exam, or the what do you call it even? I don't know. It's really just a marker for you to see how you're doing. Not going to count towards your grade. But anyway, there's the exam dates and the drop date. Those won't change as far as I know. We'll have class participation. That comes from your clickers, up to 50 points class participation. Most of you will max out that. Some of you, if you miss class a lot, you're not going to max that out. But just like last semester, if you answer a question and get it right, you get double credit. If you get it wrong, you get single credit. And at the end of the semester, I calculated your total credit as if, I calculate it in this way. I say, what if a student answers all the questions but gets half of them wrong? That student should get the full 50 points. And that's how I determine the total amount of points for each question. It's around like 0.05 or 0.1 points or something along those lines. But anyway, that's how I calculate your participation. You're going to have quiz Friday, although it's not really Friday anymore, but it's going to be your OpenStax, the tutor reading assignments, and the tutor our tutor reading, and then the assignments, we'll call them. Now the reading, you read through the chapters in the book, and it gives you questions sort of as you go along to help you sort of keep track with the material and assess yourself as you go along. And then the assignments is a quiz. That's an online quiz. It'll be 7-ish questions, and you'll have to answer them. You can work together. You can use any resource that you want on that quiz. But in the end, those online quizzes will count the same as an exam. Can I repeat that? Those quizzes, those online quizzes that you take, you know, outside of class count as a what? An exam. They carry quite a bit of weight. So, you know, I would like for everybody to have 100% on that exam. Find somebody that you know is doing well in their class and maybe work with them. Find time to work on that. You can see the questions beforehand, so you can spend as much time as you want on those quizzes. Okie dokie? That's just like last semester. I know I have a few people that are new to this class, so if you have questions about that, please see me. I'll be sending out those assignments later. I'll probably put them up either today or tomorrow. Yeah?
Is the reading assignment going to be almost like
it will be. It'll be just like last semester. It's 5 points. But you'll have other extra credit opportunities just like last semester. Okay? All right? Let's see. There's our grading, 4 exams, 50 points for class participation. That exam 5, which is those online quizzes through tutor, and then the final's worth 150 points. Makeups, as it was last semester, if you miss an exam for no excuse, you slept late, you just sort of had another exam or whatever, that's 15 points deducted from your grade automatically. And then 3 points for every day until you contact me. Usually I'm banging on your door the day that you miss it, so that's not usually an issue. But 15 points right off the top, okay? So don't miss the exam. If you've missed for some university activity, you know, sports or conference or work or whatever, we'll deal with that. Just bring me documentation. Or if you're sick, bring me documentation. But, you know, just make it to the exam. You guys do a really good job of that, by the way. You guys did an excellent job of the students just coming to the exam. I had very few people miss last semester. All right, any questions about the syllabus? Yeah, Ashley?
Is it like you have to re-register this semester?
You do. I'm going to send you out an email. You will need to enroll in the course. I put a link on Moodle. I haven't told you about it, but it's there on Moodle for you to enroll in the course. Now, if you already have an OpenStax account, you still keep that account. And I have instructions. I'm going to send you an email about it, and then all of you too. All right? Does that answer your question? Any other questions about that? Everything's going to track along a lot like it did last semester. If you want honors credit, I don't know when that application is due, but there are some ideas here for honors credit in this class. If you have your own ideas, then by all means bring them to me and we can deal with that. We can work with that. There's some stuff here about tutor, more about that coming. And those of you that are new to this class or that haven't experienced with tutor before, then I'll send an email out about that later. There's a workbook. I'll post our concept test, those questions that I asked in class here. Don't worry about the online quizzes, but if you want to go to this site for the online quizzes, I have links for all the screencasts that the online class uses, which covers the same content that we cover in here. So if you miss a day or whatever, you can go to this site and sort of pick up where you missed. But I recommend students that do well come to class. And I know you guys come to class. I get like 90% of y'all come every day, and that's awesome. It's like nothing on campus, because you know what? Y'all are what? In the world. Okay? You're awesome students. All right, this is an equation sheet. We'll have this all semester for every exam. I'll just print it out and put it on the back of your form like I did last semester, but you'll have it from the very beginning. We sort of have more equations this semester, so, we're not really about memorizing equations. Those will be on your form and for the exam. I'll go and print it out and just put it up on your cupboard just to be familiar with what's on it. It's in the back of your workbook too, I think. Am I right about that? Yeah. Old exams and their solutions are here. We're not going to have weekly help sessions, but as we have help sessions, I'll post them here. And these are our class sessions, so like I'm recording right now. So I'll post this. And then you can catch up where you missed, if you missed anything. And then there are some online textbooks here. If you're the kind of person that likes paper in their fingers, to read a textbook, I have a bunch. If you want to borrow a textbook, please come by. I'll let you borrow one for this semester. Not many of you are those kind of people, but I know there are some of you that like textbooks. Okay? Any other questions? No? Listen, I'm really excited about this semester. It'll be a good semester. We got a good crop of students here. I know that y'all are awesome. Let's see. Let's get started then. Let me sum up chapter 2 in like 2 sentences. Not chapter 2, chapter 1. Thank you. So in chapter 1, we're going to deal with electric forces and fields. Well, I'm going to write this down. I'm just sort of summarizing it for you, so to give you an overview. With forces, we're going to do 2D vectors. But you know what? We've done 2D vectors before. Most of you are probably okay with it, even still now. But we're going to revisit it one last time before we move away from those. We'll do 2D vectors. We're going to see Coulomb's law. You've probably seen Coulomb's law. It's that equation that looks like this, F equals K, QQ over R squared. It describes the force between two charges. And then we're also going to look at fields. We're going to look at fields, how they describe a force per charge. We describe our fields, our electric fields, as F over Q. And then we're also going to look at field lines and how we interpret field lines to describe the force of a charge onto another charge. All right, so that's sort of this chapter. It's one of the more difficult chapters, I find. Once we get into circuits, some people really like circuits and some people don't. But I find that this chapter and the next chapter are sort of the more difficult chapters. All right, so just sort of keep that in mind as we go through, that if you feel like you're falling behind, just know that you're in good company. That a lot of students feel sort of lost right at first. But also know that it's, what's my job? You know what my job is? The what? No, what did you say, Jacob? It's to help you succeed. Right. So if you feel like you're falling behind, then please, by all means, come see me, shoot me an email, come to my office. I'm available to help you in the class if you need that extra help. And that's my job, so let me do my job. Some of this chapter you'll remember from grade school. All right, so we often experience the presence of charges. Like, for example, if we have our hair standing up, especially you women, especially you that are blonde and sort of have lighter hair, because that hair is a lot, darker hair is heavier. Did you know that? Dark hair is heavier than light hair. And so lighter color hair, like blonde hair, will sort of stick out more because you get charges on them and it causes them to sort of, you ever done that before? You read charges in your hair? You can feel it in your hair? Yeah. Okay, so we can experience the presence of charges with hair standing. If we shuffle our feet, listen, I went to a boarding school in high school. You don't know this about me? And I had a roommate, Chris Reitz. He was kind of square. You know what I'm talking about? Like, we'd all stay up really late studying and stuff. Not him, man. He could have bed at like 10 o'clock. And he was my roommate. He's also like my best friend. But I like to mess with him. So sometimes at night, like at 12 or 1 o'clock, I'd be looking over at him. And I would get up and I'd shuffle my feet. And I'd walk over to him and put my finger next to his ear. Have y'all done this before? Your roommate? Yeah. You have? Are you serious? And then you can, one night I did, you can actually see the spark jump from my finger to his ear. Isn't that amazing? You can see it, he just sort of twitched. He didn't wake up, so I did it again and again. But we'll see some charges next time. We'll actually play around with some charges. But what I was doing there is I was shuffling my feet and rubbing electrons, negative charges, off of the carpet, and they go onto my feet and they come onto my body. And then when I touch them on his ear, they jump from my body onto his. Right? So we've all experienced these. By the way, these things don't work very well on humid days. And you might have experienced that, like, for example, on a really dry day, you find that you're getting yourself shocked, like every time you get into your car on a really dry day, which doesn't come very well around here. But why is it that charges don't transfer very well between people on humid days? Jacob? Right, okay, it has to do with water. What is water? What type of molecule is it? It's a polar molecule. Anybody know what that means, to be polar? That's right. So in a polar molecule, there's not an ion, but one side is slightly more positive or negative than the other side. And so water, because it's slightly more negative or positive on the other side, as it travels through the atmosphere and it comes all around you, it pulls all that excess charge off. So on humid days, when water, which is a polar molecule, it'll pull the excess charge off of you. Let me write that down. So water is a polar molecule. So slightly positive or negative on either side. And it pulls excess charge from your body. Carries it away. All right? I know that y'all don't do this, because, you know, you're not married, but sometimes when you kiss somebody, you get a charge. Y'all, that ever happen? Oh, right, it's happened to me and my wife. And by the way, it's our 14th anniversary today. I'm here with you people.
Well, so is she.
That's ORC, right, yeah. All right. So when a material has excess positive or negative charges, we call that it's electrically charged. And just some basic properties of charges. We have both positive and negative charges. Like charges will repel from one another. So for example, if I have two positive charges here and here, they're going to move apart from one another, or they'll be repelled from one another. Likewise, if I have two negative charges, they'll repel from one another. Opposite charges will attract. So for example, if I have a positive charge and a negative charge, they attract to one another like that. Also, charge is conserved. It is not lost. Or let's say it is not created or destroyed. That's what it means to be conserved, that you don't make new or take away old charges. You can move charges around, and in fact later in chapter 4, we'll talk about how charges can move into the earth, and it's sort of like they're lost, but they're just really moving into the earth, which is like this vast reservoir of charge. And then lastly, charge is quantized. Right? To be quantized means that it comes in particular quantities, and a charge has a fundamental unit, and the fundamental unit of charge is 1e, and 1e, the unit rather, e, is equal to 1.6 times 10 to the minus 19. The SI unit for charge is the Coulomb, which is capital C. So the fundamental unit of charge is this 1.6 times 10 to the minus 19. You've probably seen that number, even if you don't remember it, I'm pretty sure you've seen it, because that's the charge of an electron, and it's also the charge of a what? Proton, right. Electrons and protons have the same charge. They have very different masses, of course. Which one is heavier, the proton or the electron? The proton is a lot heavier than the electron. All right, so those electrons zoom around the nucleus, but the protons don't move around that much. All right, to be quantized then means that a charge can be plus or minus 1e, it can be plus or minus 2e, it can be plus or minus 3e, and on and on and on. When you have a charge, you have a discrete number of electrons or protons. You can have 1 proton, 2 protons, 3 protons, but you can't have 4.5 protons. Like, the fundamental unit of charge is always going to be equal to this value times some integer. Most of that you've probably seen. Let's try this quick test. Which of these values, oh, and by the way, we're using frequency code AA. That's the default on your clicker, but that's the one we'll be using. Which of these is not a valid charge? We'll stop at, say, 25. It is B. B is the right answer. Look, guys, what is this charge? 1.6 times 10 to the minus 19. What constitutes that charge? 1e, right? Or 1 proton, right? Because it's positive. How about this one? What constitutes this charge? This minus 3.2 times 10 to the minus 19. Right, 2 electrons are negative 2e, if you want to think of it in that way. This one, like if you do 54 divided by 1.6 times 10 to the minus 19, this is like a whole bunch of protons, right? I don't know what the value is, but it's a huge number of protons. But this one, let's see, it's protons. It's not 1 proton, not 2, not 3, because 3 would be 4.8 times 10 to the minus 19. And then 4 would be 6.4 times 10 to the minus 19. So it's somewhere between 3 and 4 protons, but you can't have anywhere in between 3 and 4 protons. So B is the right answer. And if you want a formula to figure this out, you could say, well, 5.4 times 10 to the minus 19 divided by 1.6 times 10 to the minus 19, you would find that this is equal to 3 point something. I don't know what it is, but that something is what's important. That it's neither 3 nor 4 protons, it's somewhere in between. And so that means that that's not a valid charge, because charge is quantized. It comes in discrete quantities. All right, so how do objects become charged? Objects become charged by transferring electrons. Not protons. Why is that? Well, protons are tightly bound in the nucleus. They just don't move around very much because they're so tightly bound in that nucleus. But the electrons, man, you can rip electrons off all day in various ways, either chemically or mechanically. But we transfer electrons, which are easily stripped from the nucleus. Or not from the nucleus, from the atom or molecule. Because you got the nucleus here, and then the electrons are in the nether regions, and so you can come off and pick one off through various methods. I'll talk about this in chemistry. Okay, so some conductors. In conductors, we're going to deal with conductors a lot this semester, but in conductors, electrons move freely. In response to other charges. And so what are some examples of conductors? Metal, right? Mostly metals. Water can be if it has impurities, but mostly metals. Basically, if something's a good conductor of heat, then it's also a good conductor of electricity, because they operate by the same mechanism. How does a material conduct heat? Well, if you have, say, a metal rod and you touch one end of it to the fire, the electrons in the rod are excited and they move back and forth, and they transfer that energy all along the metal rod. So a metal rod is a good conductor of heat because its electrons move around freely in response to the other charges. So the hot charges down on that end in the fire, they transfer the heat all the way up to your hand. In a similar way, metals are good conductors of electricity because their charges respond to other charges. And the electrical energy coming in one end of the conductor will move all the way through the conductor because those charges transfer that energy. So mostly metals. And insulators, the electrons do not move freely. They're more tightly bound just because of the atomic structure. Some examples of insulators. Okay, yeah, plastics. That's why we use them, to in our houses to shield our wires. What else? Rubber. Wood is a good insulator. Again, almost anything that's a good insulator of temperature or heat is also a good insulator of electricity. And semiconductors, we're not going to get into semiconductors here, but just sort of know briefly what it is. It's a material that becomes a perfect conductor under certain circumstances. We'll talk about this in chapter 4, I think, briefly, but mostly we won't deal with these. All right? So in a semiconductor, you can have it, it's a material where it doesn't conduct electricity at all, and then if you change something about it, which we'll talk about later, it becomes a conductor, a very good conductor of electricity. And so that has implications for various things that we use in life. Let's see, if one area of a conductor becomes charged, the charge evenly distributes itself across the entire surface. And when an insulator becomes charged, the charge stays in place. All right? So this class is sort of like an insulator. Like we imagine that we're all charges, say we're all positive charges, you know, positive kind of people. But you're largely an insulator because you don't move around. Like what if I was like a big charge and I was positive and you were all positive? What would happen if I walked down the aisle and we were actually in a conductor? What would happen here? Y'all would all zoom away from me, right? Or if I was a negative charge and y'all were all positive, y'all would all zoom towards me. And also, if this was a conductor, we wouldn't have all this empty space back here. That we would all be organized equidistant apart. Y'all follow me? Like we wouldn't have all this cluster of charges up here because if you were all positive charges, you'd be repelling one another. And you repel one another such that everybody would be evenly separated in this room. Next time, I want you to come into this room and sit as if it was a conductor surface, not an insulator. Think about that. Okay? No, I'm just joking. You don't have to do that. But y'all follow what I'm saying there? That if this were a conductor, you would all be repelled from one another if you were all positive, and you would all be equally spaced because you have all these forces acting upon you. All right, we sort of have some ways that we talk about things as they become charged. So charge on a conducting sphere. If you dump some charges onto a conducting sphere, they separate evenly. However, if you dump charges onto an insulator like this, they just stay right where they are because they don't move around in the insulator. We have two different ways of charging by conduction and charging by induction. Charging by conduction requires contact. So let's say that you have this charged conductor, it has negative charges on it, and it comes up close to a neutral conductor and actually touches. Those negative charges will now go onto the surface and spread around, and then once you take away the charge rod, this no longer has any charges on it. It's transferred them all to the sphere. All right, that's called charge by conduction. Charge by induction doesn't require contact. Let's say that we take a conductor like this. It has equal numbers of positive and negative charges. Right? It's neutrally charged. It's no net charge. And then let's say that we bring a negatively charged rod up next to it. What's going to happen on the conductor is you're going to get your positive charges over here and your negative charges over here. And then, this is called a ground. This is just a wire that leads away and goes to the ground. All those charges are sucked off of there. So our negative charges now traipse down into the earth, and we're just left with the positive charges. There's our negative charges over here. So in the end, after you take this rod away, you're going to have a positively charged sphere. That's called charge by induction. And you can do that where you have no contact between the surfaces, but you have this sort of drawing away of charge. Okay? We see this in the human body. In fact, you guys are probably, you've taken, like you study the nervous system yet in some of your classes? Yes? No? Okay, well, the nervous system, you talk a lot about potentials and electric fields and how these charges move as they move through the neurons. All right, let's try this quick test. In this figure, a ball is made of a conducting material. So this is like a metal ball or whatever, some sort of conducting material. You bring a positively charged rod up next to it, and this happens. It sucks it over close to it. What must be the charge of the sphere, of that conducting ball? All right, we'll stop at, ask your neighbor, folks. Y'all are split sort of evenly between the right and the wrong answer. Ask your neighbor what they put, please. Wait, not that neighbor. Ask another neighbor. All right, I'm going to stop at 110, okay? 110. We're swinging right direction. Just a couple seconds. Just guess if you don't know. Okay, good. C is right. Negative, like a lot of you put B at first. A negative would cause this situation, but because it's a conducting material, it can get an induced charge where I have the negative charges over here and the positive charges over here. So just because it's neutral doesn't mean it's not attracted. It depends upon what type of material. If this was a insulated material, what would the answer be? If the little ball was an insulated material, like a piece of wood or whatever, what must the charge of it be? It would have to be B, right? Because you don't get that induced charge set up on the material because it's an insulator. All right, so in insulators, you can get sort of an induced charge. I know I just said that, but in insulators, the charges don't move. But charges might move along the surface. I'm going to bring our Van de Graaff generator next time, and I'll show you how these charges can move across an otherwise insulating body. Charges can move across the surface. And when a charged object is brought near to an insulator, the molecules may become polarized. Like here, if I have this insulating material, I can actually polarize the charges in the insulator, where I'd have a molecule that becomes more negative on one side and more positive on the other. Like that. All right, so we can have some effect in insulators on their charges, but just not as much as we have in conductors. All right, let's do a few more. Let's see, I think I have my question here. Yeah, so consider these separate arrangements of insulating materials. What is the charge of Q1? Oh, Q3 has a negative charge. What is the charge of Q1? If Q3 is negative, what must Q1 be? And these are separate situations, so it's like two different things right here. All right, good. If you're not sure, ask your neighbor. Most of you have it right. I'm going to stop at 40 seconds. 40. I'll go to 42. Okay, awesome. A is right. As I heard some of you say, if Q3 is negative, that means this has to be positive. If that's positive, then this has to be positive. So A, isn't that what y'all put? Yeah. So A is the right answer. Yeah, so where does, listen, I know some of you have heard this joke, so don't shout out the punchline. I'm punching you. Okay? Where does a one-legged woman work? And you say what? I don't know. Where? IHOP. Had y'all heard that one before? Yeah, there's lots of the one-legged woman jokes. One day I'm going to have a one-legged woman in my class, and I'm not going to be able to tell that joke. Maybe that's kind of mean. Unless she works at IHOP. Right. All right, let's do a few more questions. We get out of here. 11:45, is that right? 11:50? I've been teaching at 4M for 12 years, folks. I know when we get out of here. All right. Two charged balls are repelling each other as they hang from the ceiling. What can you say about their charges? All right, I'll stop at 35. Y'all doing awesome. You'll see some easier questions like this on the exam too. We'll get into some more complicated stuff next time. Awesome. D is right. They're either both positive or both negative because they're repelling from one another. Hey, why do gorillas have big nostrils? You ever seen their nostrils? Those things are huge. You know why they have big nostrils? Got big fingers. Okay, from this picture, what can you conclude about the charges? This is very similar to what we had before. These are separate situations. All right, I'll stop at 40. All right, good. C is right. All of the same charge. I'm going to hold back on the joke. Otherwise, we'll be all done. Let's try this one. Metal ball. Oh, this is the same as we had before, but I'll let you go ahead and do it. All right, I'll stop at 30. 30. No, come on, folks. It's either negative or neutral, right? It's the same question as we had before. So it can be neutral. Of course, if it's negative, they're going to attract because it's positive and negative. But it can be neutral because then I'd have negative, 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 positive, positive, positive. You'd get this separation of charges on this conducting sphere. Oh, let's go back. Just sort of. I'm sort of talking about this in a lackadaisical way. Because I'm talking about, well, all my protons move over here and all my electrons move over here. Of course, that's not really what happens. You suck all the electrons over, and you leave an excess of protons over there. But no protons actually move over. It's just you're taking away the electrons, and it leaves an excess of protons. All right, the protons don't actually move. Let's see, I think we have another moment. This is charging by induction. I know the charges on the bottom. Those are question marks down there. All right, I'm going to stop at 32. 32. Okay, C is right. I get these charges set up, negative, positive, and so it stays negative, positive. So C is the right answer. What time have we got? Let me check. Where's the clock? All right, hold on. Oh, there you go. Y'all have a great day, okay? What class is this? Oh, geology.